So, we have been looking at this best case Nash equilibrium, right, best case and strong so we will look at what we call strong Nash equilibrium today. This is what is called okay. So, what was the price of anarchy? What was the price of anarchy? It was worst possible cost on PN, on pure Nash equilibrium, right, divided by optimum cost by what do you call optimal performance or by system something. Okay, so basically let us say worst possible cost of this, and this is optimum cost of optimal outcome, okay, cost of optimal outcome. And then we defined study what we call price of stability, which was best possible cost of PNE divided by cost of optimal outcome. And then I proved the following theorem modulo one statement, what I call price of stability theorem. What did we prove for a price of stability? That in every network, cost sharing game, with k agents, right, with k agents there exists a PNE, a pure Nash equilibrium, right, there exists a PNE with cost at most hk, which is basically ln n, you can think of this as a ln n, hk times that of an optimal outcome, time that of a optimal outcome, right. So, this is the theorem we try to prove. And how did we prove? We said, hey, so the steps we had is that we defined phi of p, which was nothing but summation E in Eg, right, summation E in Ez, or I going from 1 to frequency 1 over I gamma I, where gamma E was the cost of picking that edge, right. And then this is, yeah, this is exactly what it was. So, it was gamma E by I, and this is what it is, okay. And then I showed to you that a strategy that minimizes, remember what P is, basically P, you are given a directed or undirected graph, P is nothing but like for every agent you are picking a path from origin to destination, OI to DA. So, this is like, think of this as P1 to Pk, okay. A strategy that minimizes phi is pure Nash equilibrium. This was a claim which I did not prove last night, and assuming this claim, I showed to you that if this is true, then I showed to you that phi of p, look at cost of any, look at the potential of any this thing, this is greater than equal to cost of p. Why this is greater than equal to cost of p? But because what is the cost of p? Cost of p is nothing but gamma E divided by f of E. It just does not adds, it is just like last term of this sum, right. So, rest you are adding more positive things. So, it is like, think of this way, gamma E is like 1 by f of E plus some more positive quantity, right. So, this is why this is cost. So, cost was nothing but for every edge E frequency of E is at least 1, this is what it was, right. So, this definitely does this, and we showed that this is less than equal to hk times cost of P, right, and we showed that let P denote the pure Nash equilibrium that minimizes phi. Okay, that minimizes phi. Okay, I am just trying to be slightly quicker now, just to give you a reminder of what we did last night. So, how did we prove the proof? So, we said here is the potential that we defined. We show that this is a, we will show today this is nothing but minimizes. Then we showed this, just if you, this is very simple to do this because you can take out this and then it becomes cost of P. So, this inequality is not very far. Then we say that let P denote the PNE that minimizes phi, okay, and P star be an optimal outcome. P star be an optimal outcome. Okay. So, P star is an optimal outcome and this. So, what we know about it? Cost of P is less than equal to phi of P, which is less than equal to what? Because it was a minimizer and P star is also like P star is also an element where phi could have minimized it, right, phi. So, if it does not, then we know that this is less than equal to phi P star. And now what does this tells us? For any P, this is less than this, which is less than equal to hk times cost of P star. So, now cost of P is hk times cost of P star and then we are done. Okay. So, modulo that a strategy that minimizes phi is pure Nash equilibrium, we have done the proof. So, now first thing that we will do today is to show this claim. Okay. So, now we will first prove the claim and then we will. Okay. So, why is that? So, let us start with, let us go slowly now because I am not very okay. So, suppose P minimizes phi P. So, P is some strategy that is minimizes phi of P. Now, why is P not pure Nash equilibrium? Because there exists an agent I, right, and a strategy Si for I, right, strategy for Si that if it replaces its strategy, let us say Si prime, a strategy Si in Pi with Si prime, then its individual cost decreases, right, strictly. What is no, it is not a pure Nash equilibrium, right. So, I am saying because so if you look at a there exists an agent and a strategy such that if you replace this, then its cost will strictly decrease. What it means of this? So, think of this way that if my P was P1 P2 dot Pk, so this agent chose Pi prime, Pi plus 1 and look at Pk, okay, look at this, right. So, the guy had just replaced Pi with Pi prime. So, here is the Pi, okay, replace. Now, what happens because of that? Okay. So, what it is trying to tell us is that then cost of P prime, cost of ith agent with respect to P prime is strictly less than this. Okay. Okay. So, there exists. So, now we have this P and P prime. What will be shown now to show that? So, we will show that hey, if that is the case, this happens, then cost of P prime is actually less than equal to cost of P, and this contradicts because, why it contradicts? Because P is minimizer, right? Okay. How can I show this? So this is same as showing that strictly greater than 0. Okay. What is phi of P? Okay. So what is phi of P and what is phi of P prime? So what is the phi of P? So phi of P is this function. Okay. So let E be an edge that do not belong to either Pi or Pi prime. Okay. Either Pi or P prime, then its contribution in phi P is same in phi P as well as phi P prime, right? Then its contribution to phi P and phi P prime it's same. So everything that happens if E belongs to either Pi or Pi prime. Is it fine? Okay. Now let's look at the edges. Okay. So these are the edges of Pi. Let's call this A, let's call this B, and let's call this C. A, B, and C, right? These are those. So what I mean by this is A, those edges that occurs on Pi but not on Pi prime. C is those edges that occurs on Pi prime but not on Pi, and B are those edges which occurs on both. Correct? Okay. So now let's write down the contributions of this. So what it will be? Summation. Let's write down phi of P is nothing but, now I am trying to write what is the I have anyway every other edge contribution is taken care of, right, because they just so let's focus on the edges which are here, right. So now let's try to write it. E in A, what is the contribution to phi of this? It is going to be summation I going from 1 to what is this? Frequency of E, right? 1 to frequency of E, gamma E by I, correct? Same with respect to B. Now let's write with, look, these edges can also be present in this, right? These edges can also be present in my structure, right? I have not counted them because if you look at the summation, so now there's something interesting happens. Whatever these edges are, its frequency increases by 1. These edges, right? For these, no, okay, no. So this is correct. My bad. E in C, Fe gamma E by I. Okay. So this is the quantity. Okay. And what is this quantity? Let's try to understand what this is. Nothing but minus something which is in A is missing in this, because these edges are not on Pi anymore. It means their frequency has decreased by 1, correct? Decreased by 1. Okay. So this is minus summation over E in A, or say E prime in A, okay, edges in A, same edges, and what is this? Gamma E summation over how much? I going from 1 to Fe prime minus 1, right? 1 over I, correct? Minus E prime in B, gamma E prime summation I equal to 1 to f of E, right, f of E prime, right. Why it is f of E prime? Because these elements removed got added back because of this. So, their frequency remains the same. So, this is 1 over I, okay, minus E prime in C, E prime in C, gamma E prime. What happens to them? Now, these S's frequency has increased by 1, whatever it is. So, this is okay. Now, notice that this quantity and this quantity is same. So, they cancel out each other. Okay. Now, look at this quantity and this quantity, what happens? What is left here? So, except the last term here, everything will get deducted from here. So, for each E, like maybe here it was 5, it has become 4. So, it is, this will stop at 1 by 4, that by, no, this will stop at 1 by 4, 5, that will stop at 1 by 4. So, gamma into this. So, it is just the last quantity. So, this is, so if you do this, this will become summation E in A, gamma E F E, right. And what is now, so we have taken care of this quantity and this quantity. What is this? It is frequency has increased by 1. So, what will be left? Only this quantity will be left. So, this is what? Minus E prime in C, gamma E prime, correct? This is what it is. So, this is what the quantity we are left with. But what is given to us? The only thing we know that Ci of P prime is less than or equal to Ci of P. What is Ci of P prime and Ci of P? Let us say, no, this is Ci of P prime. What is Ci of P prime? What is the cost of P prime? This is nothing but summation, right? E belongs to P prime, right? Gamma E, right? Gamma E, say frequency in P prime, okay, just for us to understand. And this is less than or equal to summation E in P, right? E in P, right? Gamma E, frequency of E in P, just for us to understand. Now, notice that the people who are in B, people who are in the B set, their frequency remains the same. So, those guys get cancelled from both sides, right. Now, what is this? So, now only thing which is left is something which is in A, which is this, correct. What is left here is something which is in C, which is this. Now, what I know, this quantity is, no, what I did, no, correct. This quantity is your here, this is what is left, and this is the quantity which is left here, right. So, I know, and this quantity is less than this quantity, which implies that this quantity is strictly greater than 0, and then we are done, right. So, we have shown to you that this is a pure Nash equilibrium, because if it is not, then you can show that the potential of phi prime is strictly smaller than the potential of phi p, because this is strictly greater than 0, the difference is strictly greater than 0, and then we are done. Okay. Okay. Okay, so this is the end of the proof for that concept. Okay. Okay. Okay.
Hi, I have a question actually.
Please ask.
Yeah, so in the second section of the proof, summation of RE by FE minus summation of RE prime minus FE plus 1 prime.
Right.
In that thing, so I did not get it. How did it become greater than 0? Because
oh, this one, this quantity, these two quantity, right?
Okay.
Yes, but we also are given that Ci of P prime is less than Ci of P, correct? Okay. So, now what is Ci of P prime? It is gamma of E Fe in P prime, correct? but this is same as saying as gamma, because whichever is in the B is in the both sides, right. So both sides so I can write it E in B, okay, E in B gamma E F E in P prime plus gamma E in C, right, F E in P prime, correct?
Yes.
Okay. This is less than equal to summation, here I can write E in B gamma E F E in P plus gamma E in A, right,
Yes.
F E in P, okay.
Yes.
Is it fine?
Yes. Yes.
This, sorry, this and this are same. For elements in B, F E in P prime is same as F E in P. So this and this term will go to cancel. So all now I get that gamma E in C, F E in P prime is strictly less than gamma E in E, gamma E F E in P, right? That is exactly what this is, no?
In that case, won't it be less than 0?
No, because this quantity is less than this. So the A quantity minus C quantity is greater than 0. Let's call this quantity X, let's call this quantity Y. What you get? X minus Y is greater than 0, where X is this, Y is this. Okay? Is it fine?
Yes, yes, thanks.
Okay, good. It was an effort. It's not hard, it's just that it's tedious. Okay, so okay, I don't know whether I should rub this or not. Okay, so I'll let me use some board. Okay, till then, maybe I'll do the proof there. Okay, so the important concept to remember is the following. So if you notice that the price of stability only talks about that there is some pure Nash equilibrium which is good with respect to my possible outcome, right? And okay, what does this tells us? It tells us that POA implies there exists one pure Nash equilibrium which is close to optimum POF. And what does POA imply? Every pure Nash equilibrium is close to the optimum. Correct? And we have already saw from our examples that POA can be as bad as K for K agents, right? By in that bit max and right, this 1 plus epsilon and K, this bit max and what was the other one? VHS example, right? So it can be as bad as this. So hoping that we can show POA is bounded by something is not, like, it doesn't seem feasible. But what people do is that look at this, it's pure Nash equilibrium. You try to find a smaller place where you can show POA kind of arguments. Like, is there a stronger notion of Nash equilibrium for which I can show that POA holds there, meaning for every equilibrium in this set, every equilibrium in this state, it's close to optimum. But the problem is this may not even exist for all that you care. It says if it exists and if the big set, then everyone who satisfies this property is close to the optimum, but it may not exist at all for all that you care. Okay? So people define some stronger notion of pure Nash equilibrium. I say, hey, look at a subset of Nash equilibrium, okay, which is satisfies additional property compared to pure Nash equilibrium. They have the property that they are close to optimum, okay. And this is the idea or notion or intuition which leads us to what is that called, strong Nash equilibrium, okay. So what I mean by strong Nash equilibrium, okay. Let us try to understand this game little bit more, okay. Can I rub these things now? Okay. So, what is pure Nash equilibrium says? That one guy cannot change the outcomes, but what about allowing more than one guy? Two people come up with, say, okay, look, let us not replace once, but let us replace two of us, right. For example, if you look at, so the other example, that opt out example was, what was an opt out example? Opt out example was, okay. So, here, okay, here why were these people not moving from here to here? So, let us try to see, okay. So, this is, let us see from here itself, maybe I can say what I mean by this. So, what, there were two equilibrium here, the two equilibrium were, what was the two equilibrium? Everyone uses VHS, 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 everyone uses VHS, VHS. Then in that, cost of any agent, cost of agent I is this agent 1. And why it is pure Nash equilibrium? Because if he decides to invariably move to this, he pays 1 plus epsilon, right. So, this is why it was pure Nash equilibrium. But suppose now two agents decides, let us be smart, and let us say agent I and agent J decides to use bitmax. Now what happens? Because the cost gets divided, for both of them, it is, for both of them, cost in P prime is less than equal to cost in P for both I and J. True? Because now they are paying how much? This is 1 plus epsilon by 2 and this is 1, right. So, now I mean, so point is that people can change the outcome, reduce their cost when you are allowing more than one member to have this, right. So, the point is, so now people, there is a strong Nash equilibrium is all about that even collective people cannot change the outcome, okay. So, now I will define it formally, what it means. So, you understand what I am saying, right. So, basically if you notice here in this example, two people, if they decide to change their strategy, it is possible, one person was not able to change the outcome of this, but two people were able to improve their outcome by collective aggregation. Is that fine? That leads to what is called strong Nash equilibrium, okay. Okay, strong Nash equilibrium. This is what is called SNE. What it says is that let S be an outcome of a cost minimization game. Okay. Strategies, okay, strategies S A prime in product of the strategy space of S I in A, right. So, now we are not talking about single strategy, we are talking about the group of agents and their collective strategies, right. So, strategies S A prime, okay, are a beneficial deviation for a subset A. It is a beneficial derivation for a subset A of agents if the following happens. What happens is that cost I, so you replace the new strategies with this in where, like you remove the strategies of A, add this strategy of this, this is less than equal to cost I of S for all I, okay, for all I in A, and strict inequality holds for at least one agent in A, right. Then we say that this is a beneficial deviation for a subset, right. Is that when I, so for example, this is a beneficial deviation for I and J, right, because look at the P prime, it is actually strictly less than for both of them. So, it is, I mean in that, but we are happy even for nobody loses and at least one person gains, okay. And B, the outcome of strong Nash equilibrium, the outcome S is a strong Nash equilibrium if there is no collision of games, no collision of agents, okay, if there is no collision of agents with a beneficial deviation. ठीक है, okay. So, I am saying that outcome S is a what do you call strong Nash equilibrium A if there is no collection of agents with a beneficial deviation. There is no subset which is. Now, notice that every strong Nash equilibrium is a pure Nash equilibrium, right, because what is pure Nash equilibrium says is that for one agent there is no strategy. Here it says why one agent, not even any subset or group of agents has any deviation strategy, right. So, every SNA is a PNA, but it is not true that every PNA is a SNA. So, this is why pure Nash equilibrium is set here and here is SNA. And now we are going to show to you that price of anarchy holds for SNA, right, meaning every strategy or in SNE is close to HK, okay. So, okay, I do not, okay. So, this is a theorem which we have to prove in every network cost sharing game with k agents, okay, with k agents, every strong Nash equilibrium has cost at most hk times the optimum, that of an optimum outcome. Is that fine? Okay. So, this is the only goal I have for today. Okay. That is all that, and then this chapter will be done. Okay. So, this is what I want to prove. Okay. Let me prepare. Okay. 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 So, okay. So, now how will you go about proving it? Okay. So, okay. So, we are going to gradually, so it is a pure Nash equilibrium, sorry, it is a strong Nash equilibrium, right. So, it says no subset, no. So, look at the proof that we did for the previous. We said, hey, look at the cost of one guy, I cannot get some p prime, so there is something interesting happens, and we use that to get something with respect to our measure, right. But now it is a SNE. So, it says no subset has this property. So, what we are going to do is we are going to get an upper bound on cost of each of these people, but by using some subsets of agents in a rightful way, right. So, first of all, let us say 1 2 k, this is my whole subsets, this is a whole subset, let us call this AK, means 1 2 k. Okay. What is the property of this, right? It is a strong Nash equilibrium, it means I cannot deviate by changing these people, right. What is the meaning of that?
In every deviation there exists one agent
Okay.
whose cost is bigger.
Okay, right. Okay. So, we fix one, this is one strong Nash equilibrium, and let P star be the optimum outcome. Okay. P star is an optimum outcome. Now, notice these are k agents, right, they can all go to P star, right. Why are they not going to P star? P star is basically choice of k paths, right, in a direct graph. Now, each of them k people, means k people can change everything, right. Why are they not changing it, right? If P star is also a path, right. So, let us think that P star is like, so P is like I mean it is best for them, but it is just not stable. the only reason they are not moving to that it is not stable. Correct? That is the only reason they are not moving, because they can move to this. These K people can move to this, because everybody is allowed to change their strategy, right? Here, S A prime. So look at S prime of A K, which consists of P1 star, P2 star, Pk star. Why are they not moving to that? Right? You get my point, right? That is because it must be that for some agent I, cost of I in P is cost of P A star, right? There exists some agent I, right? It says no, I cannot move it because why? There is a strong deviation. Why it is not going to this? Because I am not able to move from here to here move. Why? Because for this strategy it is not because for some I the cost after replacement is strictly more than cost here. That is all that I have written. So after I move to P A star, my cost strictly increases. See,
For all I, cost is equal.
maybe equal, I do not care. See, what does this tells us? It is just a contrapositive of this, right? The outcome is S in E in A if there is no collision of agents with a beneficial deviations, correct? Now what is this? When do you have a beneficial deviation? There is some strategy for a subset A of agent if this happens for every I in A, okay. Now definitely P A star is also a strategy, and that is not a beneficial deviation because this is strong Nash equilibrium. Why did P1 to Pk don't move to this P1 star, P2 star, Pk star? Because it is not a beneficial deviation for this all the K agents. What this means? This is not for a subset of agent if there exists some I for which this happens with strict inequality.
Or the second condition can also be inequality holds in all cases.
What?
Either the first condition is not satisfied or second condition is not satisfied.
Okay, so what does that mean?
That is CIP is equal CIP star for all I.
Yeah. That's fine. Will that help? So I don't think it will matter for the proof. I did not move to P A star. Why? Because either nobody gets a benefit by moving there. So as you rightly say, I am here.
Yes.
Okay, fine. Right? So it's up to us which this agent is, right? So just reorder this agent. Let's call this agent equal to K. This is the kth agent which happens. This is up to us. Okay? Okay? So we rename this agent to K. Okay? Rename this agent to K. So now let's focus on, so by AI I will mean 1 to I. Okay? So now let's focus on AK minus 1. Okay? Now that we have fixed what the kth agent is, okay? Okay. Imagine that I only have, okay? Notice, if I only had K minus 1 agents, okay, I claim, look at K minus 1 agents only, A1, 1 to K minus 1, and I claim to you that this P1 to Pk minus 1 is still a stable Nash equilibrium. Why? Because for any subset you could change. So this, if I throw away the agent K, this, let's call it what is that called, Pk minus 1 or something, I don't know, okay, P AK minus 1 is nothing but you restrict this tuple to pk minus 1. This is also stable. What does this means? Same thing will imply here. It implies that it must be there exists an agent, there exists I such that cost of I in with cost of I in P is less than equal to what it is? Cost of P star AK minus 1 times Pk, correct? You understand what I did? See, I replaced first k minus 1 is P1 to Pk star minus 1. Why did I not move to that?
All of them cannot move because PK will suffer a loss.
Right, which implies this.
K minus 1 of them, excluding PK, all of them can't move because PK minus 1 will
Suffer a loss. Yes. Correct. So it must be the this agent I such that this condition is met for all these people. Okay. Okay. So we rename this agent. Okay. So you rename this agent to k minus 1. Okay. Okay. So you can iteratively apply this argument. And what do you get? If you apply this argument iteratively on the remaining of the agents, okay, as 1 to k, such that for every I, what happens? Cost of I in P is less than equal to cost of I, where I force myself on AI, I behave like this. Why didn't I to change this? And P minus A, like delete all those places where these AIs are. That's it. This, okay? Is that fine? So this is true for all I. Now more or less we are done. Okay? Why are we done? Okay? So let's sum the cost of each agent. Okay? So let's sum the cost of each agent. So what will be this? Summation I equal to 1 to k C I of P, right? C I of P, which is, and what is this? What is this? This is actually what is the cost of P is. Cost of P is nothing but individual cost of each, right? Individual cost of P agent in this P, which is equal to what? Okay, CIP, which is less than equal to I going from 1 to k Is that fine? Okay. Now this is one inequality which is right, which is I'm bit. Let's see what happens. Why is this true? This is because, look at this, look at this, look at this, like look at this, right. Now look at an agent I, right. Look at an agent I. Agent I is agent I among AI star, like some paths, right, and you had more paths. So if you have more paths, your cost per edge can only decrease, it cannot increase, right. What it tells us, what is this? What is the cost of I if I only did Pi star? So you only took at, what is this Pi star? Say P1 star, P2, where is this? Okay, where? P1 star, P2 star, Pi star, right. Look at these paths, right, and I forget everything else, right. So my cost can only increase, it cannot decrease. Why? Because look at, my path is anyway there, but now my path frequency can decrease, it cannot increase. So if my frequency will decrease, then my cost per edge can only increase, because what was the cost? What is the cost of I of in anything is nothing but summation gamma I Fe E in Pi. This is what it is, right. So now this frequency, this anyway for any path you have to pay the cost of each edge. Now its point is whether I divide into 3 people or 10 people. So if the number of paths becomes smaller, my division becomes lesser, so I pay more, and that's exactly what it says, right. So this is all that it is, okay. So when I replaced, so I had so many paths and there my cost was, right. So this edge might be in some other paths also, so my division for that edge, the divider or the denominator could be much larger, but compared to here. So when you take a subset of paths of the given path, my frequency can only decrease, it cannot increase. If my frequency will decrease, my cost per edge can only increase.
So CRP AI star is like AK minus AI players have been removed from the game.
Right, I plus 1, 2, K have been removed, right. So look at this, what is this? Like first one is this and the rest I play like P, right, on those, like on remaining coordinates I play like this. If I remove all those, my cost can only increase, it can never decrease, that's it. Okay, not easy man, not easy, especially if I'm not used to proving these things. Like I stared, why did they go from here to here, then like okay fine, it's not rocket science, and it's right that they are not writing anything, okay. Next you will use, like I find this proof magical, so don't ask me why, how they are able to prove, I have no intuition, I'm just giving you proof, okay. So now again they define a potential phi as it was in the earlier proof with one agent. Remember, like with respect to PNE we had the phi, okay, but now we will define slightly differently. What is FEI? It is frequency of an agent, of an edge E among okay, so what is frequency of an edge? Okay, frequency, or rather FEI denotes the number of agents that use edge E, okay, edge E, agents in AI, okay, in AI that use edge E, in a path in P star, right. Look at your optimum solution. I say if I fix which all these of these agents uses this path in P star. So basically it's restriction to this. So you can think that you look at this, you forget all the paths used by other agents but AI, and you define the frequency with respect to this. That's all that it says. Okay. Okay, this is what FEI is. Okay. So now what is the phi of, okay, phi of Pi star, okay, Ci of pi star is what? What it will be? Cost of I of pi star is what? E in pi star, right? Gamma E he has to pay and his frequency here. So, it is, this is what we define FEI. Okay? What is the cost of I in P star AI? Looking at the path restricted to AI, frequency among them and the cost of edge. Is it fine? Huh?
In AI, yes.
This is FEI means in agents in AI, right? So, you just restricted your paths to the only paths, say P1 star, P2 star, Pi star, and you count everything with respect to this. We will prove this in a minute. Before we prove the theorem, is that this is nothing but phi P AI star phi P AI minus 1 star. Suppose I prove this, suppose I prove this, after this I will prove this in a minute. Now, if we prove this, then we are done. Okay. So, now what is the cost of P, right? We were interested in cost of P. So, what is cost of P, you think? Cost of P is this upper bounded by this? Cost of P is upper bounded by this? Okay. Less than equal to, what is this? Ci equal to 1 to k. What is this? Ci? Ci? P star. Is that correct? Okay. And what is that? Is this quantity? So, this is like a telescopic series. What it will be then now? Okay. No, after we prove this, let us suppose we prove this, then what it is? This is like a telescopic series. What will survive after this?
Phi P AI star minus phi P A1. Phi P AI star.
Really?
Phi P JK star.
What will be 1?
Phi P.
What will be 1? 1 will be 1 minus 0, right? Right? I equal to 1, what will be 1 minus 0, 2 minus 1, 3 minus 2, k minus k minus 1, right? So, k minus 0. And what is, so this will be C k, right? Phi minus phi of empty set, which is 0. So, this is basically this. Okay, is that fine? Phi of, and what is P A k star? This is same as phi of P star, right? Because A k is all the k agents, right? So, this is this. Now, what did we prove? Okay. Oh, here. Cost of P, a strategy that minimizes phi is like any, this is also pure Nash equilibrium, Pne, Sn is also Pne. So, cost of P is less than this, which is Hk times cost of P star. Yeah, done, right? Cost of P is less than or equal to Hk times cost of P star. We are done. Okay. So, modulo this question mark, we are happy. But why is this true? It will just follow from the definitions. Okay. So, what happens? Let us see. I think it is not very far, not very difficult. Okay. Okay. Look at this. So, first of all, what is left on these things? Okay. Okay. If an edge does not occur on Pi, it does not matter. If an edge does not occur on the path Pi, it does not Pi star. If an edge does not occur on path Pi star, that does not contribute anything, because the frequency is same in both. Look at the paths. This is my Pi star path, correct? If an edge does not appear here, it does not contribute anything to both sides. They contribute same. You can cut them off. But now this is equal to summation E in Pi star. Let us say Fe equal to 1 gamma E, right? This is what is going to contribute, plus summation E in Pi star Fei is greater than or equal to 2, correct? Gamma E summation I equal to 1 to Fei, right? 1 over I, correct? Okay. Minus, look at the same quantity, right? What it is, right? The people who are here, they vanish because their frequency was only 1. Those edges do not contribute anything here because those frequency is 1. So, only these people contribute. So, what they contribute? This is like E in Pi star Fe was greater than or equal to 2 gamma E summation I equal to 1 to Fei minus 1. Yes?
You are not audible.
Oh, I am not audible? Hello? Am I audible?
No, sir.
Huh? Oh, wait. Here. Hello, can you hear me now? Hello? Hello, can you hear me now?
They can hear you. See that audio is gone.
It was muted, so I.
Yeah.
Amit, can you hear me? It's okay, I think.
They can hear you because you
Okay.
can see the audio.
Okay, it's fine. Okay. So, this is Fe star 2, Fe star 1 by I, right? This is exactly what it is. So, this guy anyway, like this minus this, what will you get? You will get summation gamma E. For this minus this is what? Let us write out, this is equal to summation E in Pi star Fe equal to 1 gamma E, this will survive, plus what will survive? The last term of these guys, right? What is that? So, this is going to survive what? The last term of this is like 1 equal to E Fei, right? So, basically it survives E in Pi star Fe greater than or equal to 2 gamma E Fei, right? And that is precisely this is the one. This is exactly what you had, no?
Okay, that is gamma E by 1.
Yeah, because that is gamma E by 1, and so you got this, so you are done. Okay, that is it. So, tell me.
So, if the optimum outcome is a strong Nash equilibrium, then every strong Nash equilibrium should be optimal.
Okay, what are you saying? If optimum outcome,
The strong Nash equilibrium.
right? So, if an optimum outcome is strong Nash equilibrium, does it imply? No, that is the optimum. No, it could be. Why it cannot be that? Look at two strong Nash equilibrium. Among themselves, they are HK factor away from each other, cost wise.
But if even one optimum outcome is a strong Nash equilibrium, then I pick any arbitrary strong Nash equilibrium.
Right.
I can't change it to the other strong Nash equilibrium without.
Yes, you cannot change.
So that means this should also be.
But we were not changing it, you know. We were not changing it to other equilibrium.
AK star.
AK star, was what? It was just a potential solution. It was not a strong Nash equilibrium because P star is not a P star is an optimum solution. Some potential optimum solution, right? But now I shift something. I said why? This also we could have changed it. We couldn't change it. You understand what I'm saying? We were never like you couldn't go to P star, no? You were allowed to change everything. Why? Suppose this is a strong Nash equilibrium. You cannot change from this strong Nash equilibrium to this strong Nash equilibrium because of this reason.
For some agent
Right.
but that will contradict that P star is strong.
Why?
Because for some agent strong is not.
No. So what I am saying to you, so suppose P is a strong Nash equilibrium and P star is another strong Nash equilibrium. You are trying to tell me the cost of both are same?
Yes.
Okay, at least I don't know how. Why? So forget, so not even optimum. Take any to a strong Nash equilibrium, and you are saying that their cost is same.
Given the optimum, there is a strong Nash equilibrium with octave, which is also octave.
Okay, so what you are saying, let's say, understand this. So this is my say P, it is a strong Nash equilibrium, and this is like P star, which is also a strong Nash equilibrium as well as optimum. Then you are saying that cost of P is equal to cost of P star, and what is your, yeah, this is fine because you can just change to P star and this is strong Nash equilibrium, so you cannot move anything, right? It's okay because if I move to P star, right, I can move to P star. So I just move to P star, okay, I moved and blah, blah, blah. Okay, okay. So what I okay, so what I say that why can't I move P star, because P star may be no, why can't I move P star, because P is a strong Nash equilibrium. So if I move, something will happen, correct? Deviation will happen. Okay. Now why this statement is still not true? So P, starting with P is a strong Nash equilibrium. I move to P star, I move, this is also a strong Nash equilibrium, but you couldn't deviate in P. It means at least for some agent here also this inequality will hold.
But with equality, because no, not
You understand my point, right? So if there are like these are like a Pareto optimal, right? There are 3-4 things could be Pareto optimal. I can't move from here to here, like they are maxima in their own world, right? And there is no way to compare them. This is exactly what, there is no way to compare them because I cannot move from here, I cannot move from here, right? Because by definition I can't move. If I move to here, then something went wrong. So I cannot conclude that the cost will be same. So at least I am not sure, I am not saying it's wrong or something, it's just that this arguments is not able to show that, that's all that I am saying.